So let's imagine we have an object, a particle of mass m, moving in the xy plane in a two-dimensional space, and gravity is acting in the y direction. So let's find the associated conserved quantity by the methods that we looked at last time. So the Lagrangian is m over 2, right? So it's moving in the xy plane. It has some speed x dot and some speed y dot. So, well, why not combine these together into m over 2 x dot plus y dot squared. And then we have some potential energy. So we have minus the u function, which is mgy. So we have an mgy function. And so we can do dl by dx dot. And that is mx dot, dl by dy dot, and that is my dot, and sorry, there's nothing more to do there. So the quantity we were looking at before is L minus the sum of the q dot times dl by dq dots, summing over j, which in this case becomes mx dot squared over 2 plus m over 2 y dot squared minus mgy minus mx dot squared minus my dot squared, which is equal to minus mgy minus 1/2 m times x dot squared plus y dot squared. And of course, that's minus potential minus kinetic. That's just minus the energy. So that's the conserved quantity. We should notice that this is not treating space and time equally. So if we want to incorporate relativity into the Lagrangian formalism, then the quantity we want is this quantity. So this is the Lagrangian density, and we integrate that over space and time. And so the generalization of this is the coordinates x mu are both space and time coordinates, and so we have derivatives of dl in the mu, call it phi, minus dl by d phi equals 0. And mu goes from 0, that's usually the time, then 1, 2, and 3 are their spatial indices, and so we're doing space and time generalization of this thing. And so if we want to do relativistic theories, and we want to start with the Lagrangian formalism, here's where our equations of motion will come from.